Welcome to Maths with EJD. We're still talking about real analysis, and here we're talking about differentiation. Now, of course, I already have a playlist on basic calculus where you can see a kind of numerical approach, a computational approach to differentiation as much as possible. And here, in the case of real analysis, things are a bit more abstract. So this is more like these are the laying blocks for whatever you see as that computational kind of differentiation. So let's go ahead and look at what this looks like in the realm of real analysis, talking about differentiation. So in real analysis, differentiation formally captures the instantaneous rate of change of a function with respect to its input, extending the intuitive geometric notion of the slope of a tangent line. So the idea of differentiation comes from the idea of slope, basically, because at the end of the day, if you take the slope of a line, so it's more like you have a line wherever it is facing, you draw a line, and then you then take you take a vertical part and a horizontal part. At the end of the day, you want to see your slope is y2 minus y1 over x2 minus x1. Y2 minus y1 is definitely changing y, and x2 minus x1 is changing x. So slope is changing y over changing x. And that's where the whole idea of the y dx comes from, changing y over changing x. So that's differentiation for you. So for differentiation, there are some core statements in the realm of real analysis. First of it is what you call the Rolle's theorem. Rolle's theorem. So the Rolle's theorem says that if you have a function f which maps a closed interval ab to the real number system, so that means the function, of course, is closed. That's what we're saying. So which maps ab to r. So if it is continuous on the closed interval ab and it is differentiable, so you see it's the function the function f is continuous on the closed interval ab, and it is differentiable on the open interval ab. So those are the two premises. The function f is continuous on the closed interval ab, and it is differentiable on the open interval ab. And in that case, we can say that, and then the third premise is that f of a is equal to f of b. Then there exists a small c, a c, which belongs to the open interval AB with f prime of c equals 0, right? That is one of the key statements for differentiation. Of course, like I said before, the whole idea of differentiation is from the idea of slope, where you say y2 minus y1 is equal to, where you say slope is equal to y2 minus y1 over x2 minus x1. Or if you say f of x1, f of x2 minus f of x1 all over x2 minus x1. That's the whole idea still. So Rolle's theorem tells us this now. Of course, this can be proven numerically. I mean, if I give you an interval 3 for and a function, so all you just need to do is to verify that the function is continuous within the closed interval, and then it is differentiable on the open interval. That's excluding the a and b now, and then f of a is equal to f of b, and then you can now go ahead and look for a particular c that lies between a and b, such that f prime of c is 0, like that. Then we have the mean value theorem. Having talked about the Rolle's theorem, we have the mean value theorem, which tells us that if you have function f, mapping the closed interval ab to r, is continuous on the closed interval ab and differentiable on the open interval ab. Now we don't need that third premise that f of a is equal to f of b for mean value theorem. That's the difference between this one and Rolle's theorem. One of the differences, right? Then we now have a c belonging to AB such that f prime of c is equal to f of b minus f of b over b minus a. So in the case of Rolle's theorem, so you need three premises. For mean value theorem, you need two premises before you now look for the c. And then the different in getting the c for the Rolle's theorem, the c is such that f prime of c is 0, but in mean value theorem, the c is such that f prime of c is equal to f of b minus f of a all over b minus a, like that, right? And then we go ahead and we have the Cauchy's mean value theorem, CMVT. So if f and g, two functions, mapping closed interval to the real number system, are continuous on the closed interval AB and differentiable on AB, the two premises, then we have a C belonging to AB with, this whole expression, GB minus GA times f prime of C equals f of B minus f of A multiplied by G prime of C, like that. Okay, so if G prime of C is not equal to 0, then we have that f prime of c. So we can rearrange this, and we have f prime of c over g prime of c equals f of b minus f of b over g minus b, g of b minus g of a. That's the Cauchy's mean value theorem. And then we have a very nice idea again about it's called the L'Hopital's rule, and it is based on the Cauchy's mean value theorem, CMVT. Okay, so for the L'Hopital's rule now from the Cauchy's mean value theorem, so 0 over 0 form local version. So this whole thing is about limits. L'Hopital's is about limits. So the first thing you do in looking for limits is substitute directly. So if you substitute directly and you get infinity as your result, or the limit is not defined, then Rolle's theorem tells you that you can go ahead and differentiate the numerator and denominator independently, and then substitute the value again. You keep doing that until you get until you exhaust all the options, and you either find a limit or you actually have undeniable proof that the function does not have a limit. Okay, so suppose fg are differentiable on ab, and then g prime of x is not equal to 0 on AB, and then the limit of f of x as x approaches a plus is equal to limit of g of x as x approaches a plus equals 0. So that means the limit is 0. Then the limit of f prime of x over g prime of x as x approaches a plus is equal to L, belonging to the the complement of the real number system, I believe. That's R cap. Then we can say that the limit of f of x over g of x as x approaches a plus is equal to L in that case. So, and in the case of computation, you can check the basic calculus playlist for L'Hopital's rule. So in that case now, we have to keep differentiating the numerator and differentiation and the numerator and denominator independently until you get the decisive limit, or until you establish that there's no limit. So analogous statements hold for x approaching a minus and two-sided limits, and for infinity over infinity with limit as x approaches the absolute value of g of x equals infinity, like that. And we have a key hypothesis here, differentiability on a punctured neighborhood. So g prime of x not equal to 0 there, and existence of derivative ratio limits, or use lim sup on lim inversions, like that. So we have, those are like some key hypotheses in that realm. Then we have Taylor's theorem with remainder, right? I think I must have talked about Taylor's theorem under sequences and series or so. Yeah, I must have done that. So you want to check that out too. So let f be n plus 1. So let f be n plus 1 times differentiable. So that means you can differentiate f n plus 1 times on an open interval containing the closed interval a comma b. Then for each x between a and b, we can say that f of x is the summation from k equals 0 to n of f fk of a over k factorial x minus ak plus Rn plus 1x. So here we have the Lagrange stroke Cauchy form, which is Rn plus 1 into x equals f n plus 1. That's the n plus 1 derivative of f, evaluating that at psi all over n plus 1 factorial multiplied by x minus a raised by n plus 1 for some psi between a and x. So then we have the Peano form at a. If f rather belongs to c raised by n near a, then we can say that f of x is equal to summation from k equals 0 to infinity of f, the kth derivative of f evaluated at a divided by k factorial into x minus a raised by k plus, the error term now, o into x minus a raised by n, as x approaches 0 in that case. That's Taylor's theorem with remainder. Then we have convexity and monotonicity via derivatives. So here we say if f prime of x is greater than or equal to 0, that's the first derivative is greater than or equal to 0 on the open interval AB, then we can say that f is non-decreasing on the closed interval AB, right? F is a decreasing function, is an increasing function, or a zero function, so to speak. So f is non-decreasing on this. And if f prime of x is greater than 0 everywhere and f prime is continuous, then we say f is strictly decreasing because we don't have that equality part there. All right, that's talking about convexity and monotonicity via derivatives. Okay, then if f prime of x is greater than or equal to 0 on a comma b where defined, then f is convex on ab. So f prime of x, that's f is convex on AB. Conversely, if is convex and F prime does exist, then F prime is non-decreasing. So, and that is why if you want to test for the nature of points in calculus, so we differentiate, we equate to zero, we get the values, and those values we differentiate the second time, and then we substitute. So if you substitute into the second derivative, the derived values of x that you get after differentiating, if you substitute them into the second derivative, it tells you if the point you are dealing with is either a maximum point, a minimum point, or a point of inflection, right? So, so you can have, if you get point of inflection, if you equate f prime f prime prime of x, if you equate that to zero, then we have proof sketches like this. So for Rolle's theorem, so Rolle's theorem implies the mean value theorem. So if you want to prove Rolle's theorem, you need to use, I mean, if you want, you can prove Rolle's theorem because it implies, using the idea that it implies mean value theorem. So for instance, if you say, let M be the minimum value of F and M is the maximum value of F, the big M now, small m minimum value, big M, maximum value of X on the closed interval AB, which exists by continuity. So if for some reason the minimum value is equal to the maximum value, then we can say that F is a constant function. So in that case, you can pick any C of your liking, right? So if that doesn't happen, if M is not equal to M, I believe, otherwise the extremum occurs at an interior point. By Fermat's lemma, F prime of C will now be equal to zero in that case, right? So the mean value theorem then, for mean value theorem, you now apply rule to h of x equals f of x minus L of x, where L is the second line from A, comma, f of A to B, comma, f of B, like that. Because, for mean value theorem, you need something like f of A minus f of B minus f of A over B minus A, something like that. Then you have the Cauchy's mean value theorem. In this case, you need to apply rule. So to apply rule, now you have h of x equals f of b minus f of a, g of x minus g of b minus g of a multiplied by f of x. So since h of a is equal to h of b, rule gives h prime of c, which is 0, yielding the Cauchy's mean value theorem. Then you want to prove the L'Hopital's rule from the Cauchy mean value theorem for the 0 over 0 case. So for x near a with x not equal to 0, of course, x is close to a, but it is not exactly a. So we apply the Cauchy mean value theorem and close interval x comma a to f of g, then we have f of x minus f of a over g of x minus g of a, which is equal to f prime of c of x over g prime of c of x for some c of x between x and a. So with f of a equals g of a equals 0, this becomes f of x over g of x equals f prime of c of x all over g prime of c sub x rather. So if f prime of g prime, approaches the limit L as x approaches a, then we say that c of x approaches a, and hence f of x all over g of x approaches L. So, and that confirms the L'Hopital's rule. So this is like the foundation of the L'Hopital's rule that we can easily just go ahead and differentiate the numerator and the denominator 10 by 10, and we keep substituting the value towards which c of x is tending until we get a particular limit or until we establish that the limit does not exist. Then we go for Taylor with Lagrange remainder. So here we define phi of t to be f of t minus p of n, p sub n of t minus lambda into t minus a n raised by n plus 1. Then we observe, so where p of n is the degree n Taylor polynomial at a, all right, and choose lambda so that phi of x is equal to 0. So we observe that phi of k of a is equal to 0 for k equals 0 up to n. By repeated Rolle's theorem, there is psi between a and x with phi, the n plus 1's derivative of phi evaluated as psi equals 0. Thus, f of n plus 1 of psi minus n plus 1 factorial lambda equals 0 implies that lambda is equal to f of the n plus 1 derivative of f evaluated as psi all over n plus 1 factorial. And then we go on to the convexity and monotonicity. So if f prime is greater than or equal to 0 on the open interval AB, we apply the mean value theorem on any closed interval xy, which is a subset of the closed interval AB, such that f of y minus f of x is equal to f prime of c into y minus x is greater than or equal to 0. Then if f prime prime of f prime prime is greater than or equal to 0, then f prime is non-decreasing following the mean value theorem applied to f prime. Hence, f is convex by the supporting line slash average slope characterization. So then we talk about consequences and techniques. So we have the mean value inequality. If the absolute value of f prime is less than or equal to m on the open interval AB, then we say that the absolute value of f of y minus f of x is less than or equal to m into y minus x. This gives a Lipschitz bound. Then we have the sign of derivatives controls monotonicity. So if f prime of x is greater than or equal to 0 on a comma b, then f is non-decreasing. But then if f prime of x is less than or equal to 0 on a comma b, then f is non-increasing, like that. And then we talk about convexity. So convexity talks about characterization characterization of convexity. So f is convex if and only if second lines are below the graph. So that means f is convex if second lines lie below the graph, and if the lines lie below the graph, f is convex. So if you want to prove convexity for f, so you have to show that the second line lie below the graph, and then you also want to show that if the second lines lie below the graph, then f is convex, two-way. So if f is differentiable, tangent lines support the graph. So touch but stay below, right? Then you have the Taylor error control. So if the absolute value of the n plus 1 derivative of f is less than or equal to k on the segment from a to x, then we have this expression that the absolute value of r sub n plus 1 of x is less than or equal to k over n plus 1 factorial into x minus a raised by n plus 1. And then we have the Dabu property of derivatives. So derivatives satisfy the intermediate value property, even if discontinuous. This is useful when analyzing f prime, when analyzing where f prime takes given values, right? So that talks about the double property of derivatives. So we have some worked examples. Let's quickly run through them. So using the Cauchy mean value theorem to prove L'Hopital for the infinity over infinity form. So let f of g be differentiable on the open interval a comma infinity with absolute value of g of x approaching infinity and g prime of x is not equal to 0. Then for x greater than t greater than a, you have the Cauchy mean value theorem on the closed interval t comma x, giving f of x minus f of t all over g of x minus g of t equals f prime of c over g prime of c for some c between t and x, that is. So if you fix t and send x approaching infinity, so if f prime over g prime approaches L and the increments dominate the initial values, one obtains f of x over g of x approaching L. All right. A rigorous proof checks tails and uses squeeze stroke, limp sum, stroke limp inf arguments. And then we go on to the quadratic Taylor at A. Quadratic Taylor at A. So for f, which belongs to c squared near A, we have f of x equals f of a plus f prime of a into x minus a plus f prime evaluated at psi all over 2 x minus a squared for some psi between a and x, like that. So near A, the sign of f prime prime controls local convexity and the classification of critical points with caveats when f prime prime of A is 0. Of course, when f prime prime of A is 0, you are talking about what is it now? Maximum point, minimum point, and inflection point. Yeah, you're talking about inflection points in that situation. All right. Then we talk about convexity from second derivative. So let f of x be equal to e raised power x, then f prime prime of x is still e raised power x, and that is greater than 0. Hence, we can say that f is equal to, then we can say f is convex. By monotonicity of f prime, we also obtain the inequality that e raised power y minus e raised power y minus e raised power x is greater than or equal to e raised power x into y minus x, right? Which is the frequently used bound. Then we have typical pitfalls in the case of differentiation now, because the hypotheses really matter. So we have continuity on the closed interval AB is essential for mean value theorem and Cauchy mean value theorem. So you see, we have three premises for okay. Yeah, we have some when we talk about Rolle's theorem, mean value theorem, and all of these theorems, we see that continuity is essential. We talk about continuity on the closed interval AB, then differentiability on the open interval AB. So that continuity on that closed interval is really important. It's not just it's not a trivial premise for mean value theorem and Cauchy mean value theorem. So a function differentiable on the open interval AB, but not extendable continuously to the endpoint, can fail the conclusion on the closed interval AB. And that's why it is important that continuity should be on the closed interval, while differentiation is on the open interval. Really important. Then we have condition G prime of X is not equal to 0 near the limit is essential in L'Hopital's rule, because if G prime of X is equal to 0, then the L'Hopital's rule breaks down, because if G prime vanishes or changes sign around the point, the ratio F prime over G prime can misbehave, even when F over G has a nice limit. So that's really important to pay attention to. Then we can there's a possibility of misusing L'Hopital, right? L'Hopital's misuse, L'Hopital only applies to indeterminate forms like 0 over 0 or infinity over infinity, because it's possible for you to I mean, you have a regular function, like maybe you have something like sine x over x squared. No, maybe sine x over x squared plus one or so. And people just go ahead and use L'Hopital's rule when it's absolutely not necessary. So this is really important to pay attention to. So L'Hopital's can be misused if it is applied to a function that has a normal limit. So always ensure the derivative ratio limit exists, or use lim sup or lim inf versions. Then we have some problems with hints or brief solutions. So problem one, we have the Rolle theorem with mean value theorem warm up. So let f of x be x squared minus 3x or minus 2 to 2. That's the interval. So you want to verify Rolle's hypothesis of minus 2 to 2 and find C with f prime of C equals 0. So that's the A part now. For 0, to find C satisfying MVT. Okay. What do I do here? So first of all, you need to, okay, I want to do this so that so I can drive the point home actually. So we want to do Rolle's theorem for f of x equals x cubed minus 3x on the interval minus 2 to 2, right? And then that's Rolle's theorem for the A part. Then for the B part, we want to do MVT, okay? MVT on the interval 0, 2. So we are looking for C in each case. We're looking for C in each case. So of course, that should remind us of the conditions for each of them. After all the premises have been met, then we now resort to the conditions. So for Rolle's theorem, continuity on the closed interval, differentiability on the open interval, and the fact that f of A is equal to f of B, we have to take care of those three things. And then we now verify, we now look for f prime of C. We now look for C such that f prime of C is equal to 0. And for the mean value theorem now, we need just continuity and differentiability. We don't care about f of A equals f of B. And then we now get f prime of C equals f of B minus f of A all over B minus A. So let me go ahead and solve that, on a, like in the proper way, so that I can actually drive the point home as much as possible. Okay, this should be this. All right. And then, so I need a new page. Good. So we need to prove that, okay, what's the question again? What's the question again? Let's see. So we are talking about the problem set. So I'll just do this one as a foundation for every other thing you may need to do. So we want to verify Rolle's hypothesis for on that open interval, and then we verify the other one. Okay. Yep. So let's go now. So we have the A part now. A to verify Rolle's theorem. Rolle's theorem for f of x equals x cubed minus 3x on the closed interval minus 2 to 2. Okay, we want to verify Rolle's theorem for this. So we have to, let's take care of the premises, right? So the first thing we need to prove is um, continuity on the closed interval -2 to 2. So the function has to be continuous on that. Then we need to prove differentiability on the open interval now, not closed interval, on the open interval -2 to 2. And then 3, we have to establish that f of A is equal to f of B. Thankfully, if you can show these two for Rolle's theorem, we don't need to do it again for mean value theorem, because those two are also necessary for Rolle's theorem, for mean value theorem. And this one is not necessary for, so this is necessary for mean value theorem. We don't need this for mean value theorem. Okay, so for Rolle's theorem, we need those three. And then if those are established, then we can look for a C such that f prime of C is equal to 0. So we need all of these things. So let's go. So talking about continuity, right? So we want to look at continuity on the closed interval, meaning that, so in this case now we can pick three values. We can pick this -2, 2, and 0, right? So we want to see if we can prove it for everything in that closed interval, then we are good to go. Of course, we can't possibly take all the values, but we are looking for that one place where it fails. And if it fails in one place, then it is not continuous in the interval, basically. Okay, so uh so to prove, okay, let me change now at this point. To prove continuity on the closed interval -2 to 2, of course, we know f of x is equal to x cubed minus 3x. Don't forget, continuity is in three forms. There are three conditions for continuity. The first condition is that that f of -2 to 2 should exist. So at no point in -2 to 2 should the function be undefined. Number two, limits as x approaches any of the values in -2 to 2, all right, should always be defined. How do we put that now? So this exists, right? So I think we can use the words interchangeably. So here, this is defined. So I think the word here is defined. Okay. And then here, this limits the limits of the function f of x has to exist. Okay. And after that, for the third point is that if condition 1 is equal to condition 2. So they must be equal. So in this case now, let's switch gear. And like I said, I'm going to pick -2, 2, and 0. -2, 0, and 2. Just spread over like that. So for f of x equals x squared minus 3x, right? So we have, so let's look at the definition part now. So again, we have f of x equals x cubed minus 3x. So we have f of -2, that is -2 raised to power 3, minus 3 into -2, right? So that is -8 plus 6, I think. Yeah, so that is simply -2, like that. Then let's take f of 0. F of 0 is equal to 0 cubed minus 3 into 0. That is simply 0. Okay. Then we have f of 2. F of 2 will be 2 raised to power 3 minus 3 into 2. So there we have 8 minus 6, and that is simply 2. Okay, that's talking about, we have just taken care of this first part now. So all these functions, so all the function at all these 3 points they are defined. There's no infinity anywhere. Then let's talk about the limits now. Okay, let's talk about the limits. So for the limits, So what did I do here now? Okay, these are the definitions of f in the closed interval -2 to 2. Okay, so I mean all of them are defined, and then we move on to the other part where we talk about limits now. Okay, so for the limits, we'll also take those three parts. Normally, I want to see that limits of f of x as x approaches any of the three numbers that you have taken I mean, they actually all exist, right? They all exist. So in this case now, I'll take -2, 2, and 0 again. So I'll say limit as x approaches -2 for x cubed minus 3x is equal to, of course, what we have to do again is put -3, -2, substitute -3, 2 directly. So again, you have -2 raised by 3, -3 into 2, and that is -8 minus 6. I mean, -8, okay, 3, this is -3 into -2. That is +6, right? I hope I did all that right all the while. So this is x cubed minus 3x. Yeah, I think this is fine. This is also fine. Yeah, I think everything is good. So this is -8 plus 6. So we have -2. So we have this. Then we also have limit as x approaches -2 for, I mean, approaches 0 for x cubed minus 3x now. And that is simply 0 raised by 3 minus 3 into 0, which is also 0. And then lastly, we have limits as x approaches, limit as x approaches 2 for x cubed minus 3x. Okay. And that is 2 raised by 3 minus 3 into 2. That is 8 minus 6, and that is also 2. So we see now that if you look at this, so we have -2 when we evaluated. I guess I want to use something totally different. We have -2 when we evaluated, and we have -2 when we took the limit. Okay. The same is true for when we evaluated at 0 and when we took the limit at 0. Same thing. And then we have the same we have 2 when we evaluated at 2, and we have 2 when we evaluated at 2, when we took the limit at 2. In that case now, so I mean it means the first two conditions are met and they are also equal. So we then say since conditions 1, 2, 3 for continuity are met in the interval, okay, then f of x equals x cubed minus 3x, okay, is continuous. Is continuous on the closed interval -2 to 2. You know, that goes. So all we have been doing since is to establish this first condition, that to prove Rolle's theorem, right? We have to prove continuity. We have all we have done is the continuity part. So for differentiability, that's the next thing we need to do now. So for differentiability, so that means that the function is differentiable in the interval. For differentiability, so for differentiability, this differentiability now happens on the closed interval. So in the open interval rather. So that means -2 and 2 do not have to be involved. So in this case, I'm just going to pick -1, 0, and 1 because -1 and 2 are not involved in this case. But differentiability simply means that, you have f of x, right, equals x cubed minus 3x. So if we differentiate this, you have f prime of x equals 3x squared minus 3, basically. So we now want to evaluate this derivative at different values. So like I said, I'm picking -3, I mean -1, 0, and 1. So we have f prime at -1, that's 3 into -1 squared minus 3. So that is -1 squared is 1 times 3 is 3. So we have 3 minus 3, and that is equal to 0. So 0 is a good answer. So it's differentiable. The function is differentiable at -1. Then we take 0. So we have 3 into 0 squared minus 3. And that gives us 0 minus 3, which is minus 3. Minus 3 is also a good answer, right? Minus 3 is a good answer for sure. And then we have f of 1, that is 3 into 1 squared minus 3. Okay, so that is 3 minus 3 again, and that is also 0. So with this now, we can say since the function since the function is differentiable, or what do I even do now? So with all these things now, we can just say, therefore, the function is differentiable. Function is differentiable on the open interval minus 2 to 2. Then for Rolle's theorem, we still have a third condition. So finally, to verify f of A equals f of B. I think we've done that already because but don't forget f of x itself is x cubed minus 3x. Okay, so to verify for f of A equals f of B now, so we just say f of A. Don't forget the interval is minus 2 to 2. So we have A, B, closed interval is the same thing as minus 2 to 2. Okay, so f of minus 2 is minus 2 raised by 3 minus 3 into minus 2. Okay, so this is minus 8 plus 6, and that gives us minus 2, like that. And then we have f of 2. So f of 2 is so f of A equals f of B. That's the third condition, right? So we have 2 raised by 3 minus 3 into 2. So that is 8 minus 6, and that is equal to 2. So obviously, f of minus 2 is not equal to f of 2. So it means that rule breaks down in that situation. Okay, so I guess we'll not be able to continue because this is x cubed minus 3x, right? So if you put 3, that's minus 8 plus 6. If you put minus 2, that's minus 8 plus 6, which is 2. If you put 2, that is 8 minus 6, that is 2. And the condition is that f of A should be equal to f of B. Okay, so I think that's a condition where Rolle's theorem breaks down. Okay, so I mean, just conclude that since f of minus 2 is not equal to f of 2, then Rolle's theorem doesn't hold. In this case. So if we assume that it's held, right? So if this third condition had been met, so what would have done is would have had to, okay, like, I mean, please, you don't have to continue. I mean, this is the end of this, but I'm just trying to say that in case f of A were to be equal to f of B, right? Then you now needed f prime of C equals 0, right? And we know that f of x is equal to x cubed minus 3x, okay? So we now need f prime of x, which is 3x squared minus 3. So that means that f prime of C equals 0 is such that 3x cubed minus 3 is equal to 0. So that means that you have 3 into x cubed minus 1 equals 0. And then, of course, that means x cubed minus 1 equals 0. Maybe the easy way out is to say x cubed is 1, right? So x is cube roots of 1. So that can actually be, it can be minus 1 or 1, right? Those are the two possibilities. So, but I mean, this is not possible because Rolle's theorem broke down at some point. So, sorry, f of C. I was talking about f of C. This should have been f of C. This should have been 3c cubed. This should have been 3c cubed. Should have been 3c cubed. C cubed so that this is C and then this is C. So C is either -1 or 1, like that. And of course, -1 and 1 actually lies between -2 and 2, but that third condition doesn't hold. But interestingly, that's for Rolle's theorem now. So for the mean value theorem, we're expected to use, so for mean value theorem, again, we have f of x equals x cubed minus 3x. And then we have the interval to be 0, the interval on 0, 2. Okay. So for 0, 2, we just need to prove differentiability and continuity on the closed interval and differentiability on the open interval. Of course, from all indications, if we do continuity, right? If you evaluate at 0, we get 0. If you evaluate at, say, 1, we get 1 minus 3, that's -2. If you evaluate at 2, we get 6. That's so, and if you also take the limit, you also get the same thing. So we can already see by inspection that f of x is continuous. F of x is continuous on the closed interval 0, 2. And when it comes to differentiability, we have 3x squared minus 3. So if you put 0, you have -3, which is a good answer. If you put that for 3x squared minus 3, right? If you put 1, you have 3 minus 3, which is 0. That's a good answer also. If you put 2, so that's 3x squared, that's 2 squared is 4. 4 times 3 is 12. 12 minus 3 is 8. So we can also conclude by that token that f of x is differentiable, So if you differentiate at this point, I mean, and now the exam set, you want to write all these things I'm just saying by mouth. So f of x is differentiable on the open interval 0, 2. Okay, open interval, I shouldn't have used 0 and 2. Maybe I should have just used like 1 and 1.5 or something like that. But of course, we know it works for 1. So we don't need the fact that f of a is equal to, we don't need f of a equals f of b. But if we needed that, this is 0, 0, 2. 8 minus, yeah, we don't need that here, right? So we can then go to find C. So we now find C now. So to find C for the mean value theorem, we now have f prime of C equals f of B minus f of A all over B minus A. So f prime of C, of course, that means we need to differentiate, right? So we already know that f of x is equal to x cubed minus 3x. That means that f prime of x is equal to 3x squared minus 3, like that. So it means that f prime of C will be equal to 3c squared minus 3. So we need this expression. Then we need f of b, f of a. So we already know that we have 0, 2. So that is our a, b. Okay. So f of a implies f of 0, which is 0 cubed minus 3 into 0. And that means that f of 0 is equal to 0. We have that 2, and then we need f of 2. So f of 2 implies, f of b implies f of b. F of b implies f of 2, which is equal to 2 raised power 3 minus 3 into 2. That is 8 minus 2. 8 minus 6, which is 2. So we have f of 2 equals 2. So we need this also. So we can then finalize and say, therefore, f prime of c is 3c squared minus 3. So we have 3c squared minus 3 equals f of 2. So f of 2 minus f of 0 over 2 minus 0. Okay, so we have 3c squared minus 3. F of 2 now, we found f of 2 to be 2 already. Okay, so that's 2. F of 0 is also 0. Then we have 2 minus 0 again. So that is 3c squared minus 3 equals 2 over 2. Okay, that is 3c squared minus 3 equals 1. So that is 3c squared equals, add 3 to both sides, equals 4. Then c squared is 4 over 3. Okay, so that means that c is square root of 4 over 3. And that means that c is 2 over root 3. We can rationalize that. So c is actually 2 root 3 all over 3. Okay, that is the C we need in this case for the mean value theorem. Okay, so we go back to where we're coming from. Yeah, and we continue with that. So this is a long one, so I'll just run through the rest of the notes. So talking about some uh problem sets. So I'll have to run through this now. Where is it? Okay, yeah. So imagine this is what I've been working on all along. So this, of course, we can see that f of minus 2 is not equal to f of 2. As stated here, that's not true because this is minus 8 plus 6. That is minus 2. And then f of 2 is 8 uh, plus 6. So this doesn't hold. So we will have to look for another situation where this actually does hold. Maybe another function entirely, right? Uh, maybe would it have worked? Okay, it wouldn't have worked for x cubed minus 3x. But that's okay. Let's move on. So for CMVT to inequality, so assume f of g are differentiable on a comma b with g prime is greater than 0. So should there exist C with this whole thing? So you can try that out. Deduce that if f prime of g over g prime is less than or equal to m on ab, then this also holds. So you want to try that. So hint, CMVT, then take sup and you want to take supremum and infimum bounds. Then for L'Hopital, careful version here. So compute natural log of 1 plus x minus x over x squared as x tends to 0. Of course, if you substitute directly, this is not going to work. But if you use L'Hopital's rule, then you can get something like 1 over 1 plus x minus 1. Differentiate x squared, you get 2x. So if you differentiate the top, you get this. Differentiate x squared, you get this. If you put 0, it still doesn't work. Differentiate for that, then you get minus x over 2x into 1 plus x. As x approaches 0, you still have of course x can cancel out here now. So as x approaches 0, then you can have minus 1 over 2. So that's L'Hopital for you right there. Then you can have the Taylor remainder estimate. So let f of x be equal to sine x. So expand at a equals 0 to degree 3 and bound the remainder for absolute value of x less than or equal to 0.1. So you have this whole expression going like that. Then you have convexity test. So for the convexity test, show f of x is x raised to power 4 minus 3x squared is convex for absolute value of x is less than this. We want to check that. So what you do, take the second derivative, 12x squared minus 6, and check sign regions to see how the signs do change. Then for pathology, which is differentiable everywhere, derivative unbounded near point. So define this step function. Show f is differentiable everywhere. Show f prime is unbounded. So the hint is for x not equal to 0, f prime of x is 2x sine 1 over x squared minus 2 over x cos 1 over x squared. As x approaches 0, the cos over 1x oscillates with unbounded magnitude. So for f prime, use a limit definition, and then you can be able to show all of these things. Then differentiable but not C1, use the same f as in P6. Proof f1 exists. F prime exists everywhere, but it is not continuous at 0. So conclude f elements of C0 but not C1, that is f is differentiable yet not of class C1. Then you can also use L'Hopital versus series. So sometimes you may, instead of using L'Hopital, you can expand something in a series and see if a term cancels out like that. Okay, you can actually do something like that. Then you can do monotonicity for sign of derivative. So suppose f is differentiable on the open interval AB and f prime of x is greater than or equal to m greater than 0 for all x. Prove f is strictly increasing and globally lift it below by m, like that. So the hint is use mean value theorem on x comma y, and then you get the idea. Then convexity characterization by Jensen's inequality for C1 functions. So show that f is differentiable, is common, convex if and only if f differentiable is convex if and only if you have this expression, and connect this to monotonicity of f prime when f belongs to C2. So I think C2 should mean doubly differentiable or something like that. Then 9.7, so you have some extras. There are some common library limits and expansions for quick use. So for instance, you have the derivative of limit ln 1 plus x, that's 1 over 1 plus x. So the expansion is x minus x squared over 2 plus x cubed over 3 and up and all of that. Then sine x derivative, you have cos x. You have sine x is x minus x cubed over 6 plus error order of x raised to power 5, and cos x is 1 minus x squared plus 2 plus error order of x raised to power 4. Exponential, you have that. That's a popular one. E raised power x is 1 plus x squared over 2 plus x cubed over 6, and also and so on. You also have strong convexity. If f prime prime is greater than or equal to k is greater than 0, then f is k strongly convex. So you have f of y is greater than or equal to f of x plus f prime of x into y minus x plus k over 2y minus x all squared. Then you have a mini checklist for exams and proofs if you are in an exam condition. So you want to check continuity. So before you prove mean value theorem or Cauchy mean value theorem, you want to check continuity on closed interval AB and differentiability on AB, just like what I did in that example I did on the worksheet. Then before you do L'Hopital's, you want to verify a genuine indeterminate form. You want to be sure that by direct substitution, first of all, you either have a 0 over 0 or infinity over infinity, and that g prime is not equal to 0 near the point, and existence of the derivative ratio limit, or use one-sided lim if or lim sum version. So don't use L'Hopital's rule when you can actually use regular methods. Then for Taylor, one other higher derivative must exist on the segment. So pick the correct remainder form and bound it. So you can see for all these expressions now. So we have order 4 error, order 4, order 4. Also, this is order 5, depending on the expression you are doing, right? So you want to be sure that you pick the correct remainder form and bound it. So for convexity, if f prime prime of x exists, check its sign. Otherwise, use the second tangent criterion. Then we have some stretch problems for deeper understanding. So for Dabu, you have Dabu for derivatives. So you want to prove that if f prime exists on the closed interval, open interval AB, and u lies between f prime of x naught and f prime of x1, then there exists C such that x naught, x1 on the open interval with f prime of C is u. So hint, apply mean value theorem to f of x minus ux. Then we have the Peano versus Lagrange. So show Peano's O into x minus an remainder implies Lagrange from when f of n plus 1 is continuous, and derive the point psi via Rolle's theorem. Then you have unbounded derivative, yet literally on no interval. So modify x squared sine 1 over x squared to build a function differentiable everywhere with f prime unbounded on every open interval of R, right? So that's another thing we can do. So this has been a very lengthy one. Let me know how helpful this has been for you. And if there's something you'd like me to try out, feel free to let me know. If you have subscribed already, thank you so much. If you haven't, of course, you want to subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Okay, having done that, you can go further by clicking on join to become a member of the channel, and that comes to some special privileges. Ultimately, comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.